Hello, my name is Alin Croitoru, and together with my colleague Vlad, we will talk about the analysis done for the paper entitled Diffusion Models in Vision and Survey, which was a joint work with Professor Radu Ionescu and Professor Murbarak Shah. The agenda of our presentation starts with a short motivation and an overview of diffusion models. After that, we will go to three formulations of this type of generative models: the Noising diffusion probability models, noise condition score networks, and the generalization of the previous two via stochastic differential equations. Further, we will address the guidance techniques used for conditional sampling, and lastly we will cover the main directions of research found in the literature. Let's start with the motivation part. The motivation behind making this presentation and our survey is the recent progress of diffusion models on the image generation task. Here is an image with the number of papers published on this topic in the last years. We can see that this number is growing at a very fast pace. Let's mention a few popular contributions with state-of-the-art results on the image generation task. Diffusion models were introduced back in 2015, with good results on the CIFAR dataset. The first major breakthrough happened when diffusion models obtained for the first time better sample quality than the state-of-the-art generative adversarial networks. Other important contributions were the papers for text-based image generation, such as GLIDE, and the progress went even further with models like DALL-E 2 or latent diffusion. The latter managed to preserve the image quality of the previous works while improving the efficiency. Moreover, diffusion models have been applied successfully on multiple image processing tasks. Let's mention a few: unconditional and conditional image generation, image segmentation, text-to-image generation, image super-resolution, text-based domain adaptation, or anomaly detection in medical images. Diffusion models are well known for the quality of the images generated with text descriptions. Here are a few more examples for this use case, where you can see an impressive alignment between image context and text. Now, we will briefly overview how diffusion models work, and then we go deeper into the details of each formulation. First of all, diffusion models are a type of generative models. The sample generation is done via a process that maps standard Gaussian noise with samples from the data distribution. The mapping is implemented with small steps, at each step a small amount of noise being removed. The training consists of two processes. The first process destroys the data across multiple time steps by adding small amounts of Gaussian noise, and the second one is the reverse process, the one responsible with sample generation. It uses a neural network to estimate the noise from the image, and the respective noise is subtracted to get the image for the next iteration. Diffusion models can be categorized into three classes, according to the perspectives which introduce them: the noising diffusion probability models, noise condition score networks, and based on stochastic differential equations. Let's describe the first formulation of diffusion models, namely the noising diffusion probability models. But first, let's clarify some notations that will appear regularly in the following slides. We'll denote the true data distribution by P of x0. The 0 stands for the fact that the data is uncorrupted. It is in its original form. With this notation, we refer to normal distributions, with the mean denoted by mu and the variance sigma, and the x denotes the sample that will be produced by this distribution. The sampling from this distribution is equivalent with adding the mean mu to a standard Gaussian sample, which is scaled by the standard deviation, namely the square root of sigma. Going back to diffusion models, remember that this type of models consists of two processes, the forward process and the reverse process. The forward process starts with the data sample x0 from the true data distribution, denoted by P of x0, and it is transformed into standard Gaussian noise by adding small amounts of noise at each step. The reverse process is the actual generative process. It starts with a sample from the standard Gaussian distribution and learns to remove the noise from each step, so that at the end of the process, the result will be a sample from the data distribution. The forward process of the noising diffusion probability models is a fixed Markovian process because the image at step t is sampled from a Gaussian distribution, which has the mean close to the image of the previous step and a small variance. Therefore, over many steps T, the pure noise is obtained by gradually removing the image information via changing the mean of the Gaussian distributions, and replacing it with noise modeled by beta t. We emphasize that beta t is fixed, therefore the entire process is also fixed. An important property of this design for the forward process is the ancestral sampling. Specifically, a sample for a random time step t can be directly computed from the data point x0 by following this normal distribution. This distribution is derived by applying iteratively all the transitions until the step t. Beta hat t is just a notation for the product of 1 minus beta I, where I goes from 1 up to the current t, and note that each 1 minus beta I is denoted by alpha I. This property makes the training more efficient because we can select a random time step t and get the noisy image for that t without computing the previous unnecessary noisy images. The reverse process starts with a sample from the standard Gaussian distribution and yields data points by ideally following the transitions denoted by p of xt minus 1 given xt. The problem is that the probability distributions p of xt minus 1 given xt are intractable. However, they can be approximated with Gaussian distributions if the variance schedule of the forward process contains values much smaller than 1. Therefore, a generative model would only need to predict the mean and the covariance matrix of this Gaussian, given the noisy image and the current step of the process. Before deriving the training procedure of the generative neural network, we motivate in the following slides the need of having small beta t's. When we know that xt is created with a very small step modeled by beta t in the forward process, it becomes more likely that xt minus 1 comes from a region close to where xt is observed, which allows us to model these regions with Gaussian distribution in the reverse process. In contrast, if each beta t is large, when we observe an xt, we will be less certain where the previous step of the chain xt minus 1 was, because we could have reached xt from many more regions. The second property of the noise schedule beta t is that we need to have a large capital T, because the noise added at each step is small, but at the same time the image must be destroyed. Hence, we need to perform many diffusion steps, which is equivalent with having a large capital T. Now we can go back to describing the training procedure. Remember that we need to train a neural network to approximate the posterior of the forward process with the Gaussian distribution. The neural network must predict estimates for the mean and the covariance matrix of this Gaussian, where theta denotes the weights of the network. As a simplification, the authors of the noise diffusion probabilistic models observe that we can fix the variance instead of learning it. Thus, the neural network will predict only the mean of the Gaussian distribution. To summarize, we need to train a U-net-like neural network to approximate from a given image xt and a time step t the mean of the probability distribution from which we sample the next image. The timestamp t is represented with sinusoidal time embeddings, similar with the position embeddings used in transformers. These embeddings are processed by a multi-layer perceptron before adding them to each residual block of the U-net. We train the neural network by maximizing the data likelihood p theta of x0, which is equivalent to minimizing the negative log likelihood. We cannot minimize this directly, but we compute the variational bound as the variational autoencoders. And in fact, we can look at the noise diffusion probabilistic models as being a special case of variational autoencoders, where the forward process is a fixed encoder that produces the chain of images x1 capital T instead of the latent z, so in this case x1 capital T plays the role of the latent variable, and the reverse process is the decoder. With this analogy in mind, we derive the bound by following the next steps. We write the log likelihood as the log marginal of the joint probability of the reverse process. Then we introduce the joint probability of the forward process conditioned on the initial image x0 in the right hand side. The result can be rewritten as an expected value of the forward process. And if we apply the Jensen inequality and multiply with -1, we'll get the bound. The Jensen inequality states that given a random variable y and a cocaine function f, then f of expected value of y is greater or equal than the expected value of f of y. In our case, f is the logarithm and the random variable is the forward process. The previous bound can be further extended if we exploit the fact that the forward process is Markovian. This is the final result. You can find more details about this derivation in our survey. The middle term of this objective can be ignored because it does not depend on theta, and the last term ensures that each time step t, p theta of xt minus 1 given xt is as close as possible to the true posterior of the forward process when conditioned on the original image x0. We can stop the derivation at this form, because the Kyle divergences of the last term are between two Gaussians, so they have a closed form which can actually be formulated as an L2 distance between the means of these distributions. Moreover, the first term of the loss basically measures the reconstruction error and can be addressed with an independent decoder. But the denoising diffusion probability models paper introduced two simplifications that led to a more simple objective based on the noise in the image. The first simplification starts from the observation that the posterior of the forward process, conditioned on x0, is tractable and it has a closed form given by this normal distribution, where the mean mu tilde can be written as a function of xt and the standard Gaussian noise zt, and the variance beta tilde is a combination of beta t and beta het t. We skip the derivation for simplicity, but one must use Bayes' rule and rearrange the terms in a particular manner to obtain these expressions. Now the idea is to parameterize in the same way the mean of p theta, but instead of using the noise zt, we use some noise estimation given by the neural network. And we know that the Kyle divergence is just an L2 distance between the means of these two Gaussian distributions. And if we replace the means with these parameterizations, then we can rewrite the second term of the objective as an L2 distance between the real noise zt and the noise predicted by the neural network, given the image xt and the timestamp t. Moreover, the term is simplified even more by ignoring the time weight associated to the L2 distance. And if we include t equals 1 in the sum of the second term, then the first term of the objective is also covered by this noise prediction formulation. In conclusion, the final objective requires only the noise prediction from noisy images. This objective was named L-simple. The training algorithm is now straightforward. We sample batches of images x0, timesteps t, and noise sample zt. Then we compute the noisy images with the ancestral sampling formulation, and we pass the batches of xt and t to the neural network to get the noise estimation z theta, and finally we update the neural network using the gradient of the L-simple loss. For sampling, we repeat the following procedure for capital T steps. We pass the current noisy image along with the time embeddings to the neural network. With the result z theta, we compute the mean of the Gaussian distribution, and finally we sample the image xt-1 for the next iteration.
That was all with the first formulation of diffusion models. Let's continue with the second one. The second formulation of diffusion models is based on the score function of the probability density. Even if this perspective is totally different from the first formulation, we will see at the end that they have many aspects in common. The score function of a probability density is the gradient with respect to the input of the log density. This function tells us in what direction we need to change the input, x, such that the density becomes greater. In the image, we have an example of a mixture of two Gaussians, and the score function is illustrated by the black arrows. We can see how it points to the regions with high density. Based on the directions given by the score function, the method called Langevin dynamics starts from a random sample and applies iterative updates with the score function to modify the sample so that the result will have a higher chance of being a sample of the true distribution P of x. The last term of the update is some Gaussian noise that helps the method, in practice, to escape the local minima. Gamma is just a parameter that controls the magnitude of the updates. Therefore, a very simple generative process can be based on Langevin dynamics updates if we have access to the score function. Fortunately, the score function can be estimated by a neural network using the score matching objective for training. In practice, this is intractable to compute, and the methods used are denoising score matching or slice score matching. For example, the denoising score matching works as follows. Some small noise is added to each example of the dataset. The resulting samples x' are now coming from a normal distribution which has a tractable form for the score function, and we can apply score matching using this score as a target. After training, the neural network will provide good estimations of the true score function because we choose the noise sigma to be small. However, this naive approach has a few drawbacks linked with the estimation of the score function. Real data resides on low-dimensional manifolds, and this implies that the score function is undefined outside these manifolds. So, when starting with random points in the Langevin dynamics, those points will probably be outside the manifolds, and the estimation of the score function will be wrong because the real one is undefined. In the image, we have a mixture of two Gaussians, and we can see that for most of the space, the estimated scores are inaccurate. This means that if the Langevin dynamic starts with a point in the red zone, then the method will probably not converge to the high-density green one regions. The solution for previous issues is to perturb the data with random Gaussian noise at different scales and learn the score function of the resulting distribution. At sampling time, we start with larger noise scales, and the Langevin dynamics is used for each noise scale at a time. The result from one noise scale will then be provided as input for the iterations of the next scale. We can see in the image that this strategy helps us to cover the space much better. This approach can be addressed with a single network if we learn to estimate the score function conditions on the noise level. Formally, the new distributions are built such that the first one is approximating the true data distribution and the last one is almost equal with the standard Gaussian distribution. The noise perturbation is formally described by sampling from this normal distribution, where sigma t is the noise scale for the time step t. The score function of these normal distributions can be computed given the original image X, so all the components are available for training the network via score matching. Using the denoising score matching objective, which was previously mentioned, we obtain the final objective to train the noise condition score networks. Moreover, this objective is enhanced with a weighting function which depends on the noise level that can be used to assign higher importance to the larger noise scales. The sampling procedure of the noise condition score networks is called annealed Langevin dynamics. The parameters of these procedures are the following. N is the number of iterations of the Langevin dynamics method. These are the noise scales. And gamma, which is the update magnitude used in the Langevin dynamics iterations. The steps of the annealed Langevin dynamics procedures are the following. We sample some standard Gaussian noise. We start from the largest noise scales, which is denoted by the time step t. And then, for any iteration, we execute the Langevin dynamics updates. For that, we need some noise for the last term and the score estimation from our neural network. At the end, we transfer the result to the noise scale and restart the process. The final output is the sample obtained for the smallest noise scale. Now that we have the two formulations covered, let's go again through their losses and sampling procedures to see that they're actually very similar. If we look closer at the two loss functions for DDPM and NCSN, we can observe common aspects between them. First of all, the weighting function is missing from L-simple because it was a choice made by the author based on empirical evidence. Therefore, the two losses are actually identical from this point of view. Secondly, we can say that the two losses are different because one approximates the noise from the image and the other the score function. However, the score function is actually proportional with the negative noise, and this is compensated by the sampling procedure. From the sampling equations, we can see that the iterative updates are based on subtracting some form of noise from the noisy image. This is also true from NCSN because the score approximates the negative of the noise. Therefore, the generative processes defined by NCSN and DDPM are very similar. Further, we will see that the previous two formulations can be generalized under the same framework. The third formulation of diffusion considers the forward and reverse processes to be continuous and defines them via stochastic differential equations. The principle is the same, gradually transforms the data into noise and reverses the process to obtain samples from the true data distribution. The SDE in the forward process is called the forward SDE and basically shows that the transformation of the image X into noise is performed via very small changes in X. These changes are defined by the function f and the noise addition omega t. The noise additions are scaled with the diffusion coefficient sigma t. We emphasize that the different choices of f and sigma will imply different forward processes, and this is what happened with the previous two formulations. They are slightly different because f and sigma are different. An important result shows that the reverse of the previous forward process is also a diffusion process running backwards in time, and it is described by this SDE called the reverse time SDE. This equation is very intuitive if we think about it as in Langevin dynamics iterations, where we updated X to go from low density regions to regions with higher density. The same thing is happening here. We use the score function with the same purpose, but the formulation is generalized to the continuous case. The training objective remains the same in NCSN because the goal is to estimate the score function. The sampling is performed by employing numerical methods to solve the reverse time SDE. We will briefly show how to transform the noise perturbation of NCSN and DDPM into their corresponding forward SDE. We start with NCSN and we do it by rewriting the forward process as an SDE discretization. After that, we adapt the expression for the continuous case. So all the variables are now time-dependent functions, and the changes of these functions are now measured for an infinitesimal small change of time. A small observation for this case is that the drift coefficient is constant, being equal to 0. Similar to NCSN, for DDPM, we start from the Markovian formulation of the forward process. We replace beta t with a product between delta t and beta of t, where delta t is 1 over capital T and beta of t is beta t multiplied with capital T. So these changes are just a rewriting of beta t. They are necessary because the link with the SDE formulation will be more obvious with these notations. We extend the square root of the first term from the right-hand side of the equality with the Taylor expansion. We only limit ourselves to the first two terms of these expansions because delta t is very close to 0 and the following term would contain these values at increasing powers. After this operation, we are able to describe the changes in X in discrete setting. Generalizing this change for the continuous case, we obtain the forward SDE of DDPM. Let's see now how to use these models to perform conditional generation. So far, we saw how to use diffusion models for unconditional image sampling by estimating the score function. Another equally interesting application is conditional sampling. Given an additional input y, such as a class label or text, the task is to generate images that correspond to this input. In other words, we want to sample from p of x given y instead of p of x. One option is to train the model with an additional input y so that the model learns to estimate the score function of p of x given y. If y is a class, we can represent it as a one-hot encoding, and this representation is processed by a multi-layer perceptron before using it in the unit layers. If y is a text, we can use the representation resulting from a transformer. The second option to implement conditional sampling is called classifier guidance, which basically requires an unconditional generative model and the classifier trained on noisy images. If we apply bias rule on the conditional p of xt given y, we have this equality. But the score function uses the logarithm of the probability density, so we apply the logarithm on both sides. Lastly, if we compute the gradient with respect to xt, the last term becomes 0 because it does not depend on xt. The resulting expression states that we can compute the score function of p of xt given y as a sum between the score function of p of y given xt and p of xt. The latter is what diffusion models already learn, while the first conditional p of y given xt is what standard classifiers learn. So in order to use the score function of p of x given y in the denoising step of diffusion models, it is sufficient to have an unconditional diffusion model and a classifier that is robust on noisy images. An improvement that can be done in order to force the generation to be more precise is to add a weight to the guidance term. On the left-hand side, the guidance weight is equal to 1. On the right-hand side, the guidance weight is equal to 10. As we can observe in the figure, when the weight is large, the images are more class consistent and the diversity of the samples decreases. The main problem of the second solution is the classifier, because we need to have good estimates for the gradients at each step of the denoising process. Thus, we need a classifier that is robust to noise added to the image. This often means training the classifier on noisy data, which can be problematic. The issue is what the second guidance technique addresses, which is called classifier-free guidance. If we expand the conditional P of y given x of t with the bias rule, and then apply the logarithm on both sides, we obtain this. If we compute the gradients with respect to the noisy image x of t, we have an expression from the classifier gradients. We can use this to replace it in the classifier guidance formulation, and we obtain the following. The result is a combination between conditional and unconditional model, but with a small trick, we train a singular neural network for both cases. The two core functions can be learned at the same time by a single model. We just need that training time to discard y with a fixed probability. Discard of y is done by setting its embedding to a vector that has all the elements equal to 0. Finally, we will cover shortly the main direction of research for diffusion models. The most frequent tasks on which diffusion models were employed are the unconditional and conditional image generation. For unconditional case, the focus was on improving the efficiency and the quality of the generated images, while the conditional case becomes more popular with text-to-image generation. Besides these two tasks, this type of models were also employed in image editing and even editing based on text input, super resolution, image segmentation, anomaly detection in medical images, or video generation. Although the results of diffusion models is promising, even surprising one, the early phase of the research gives us plenty of future directions. Increasing the efficiency of sampling, multiple applications with computer vision such as dehazing, video anomaly detection, discriminative tasks, and even simulate the continuation of videos. Thank you very much for listening. If you want to find more about diffusion models, please check our survey and our GitHub page.